So now that we understand how these trees should work in theory, let's talk about how we might implement them in Python. Looking just at the top node of this tree, it has three important parts. The content, the number or name that I'm storing there, and then the left and the right children coming out. However, we can also see that some nodes have no children, may not have a left or a right child. Let's use a very simple and direct approach for encoding these trees or representing them in Python. We'll use tuples. We'll have a 3-tuple where the 3 parts correspond exactly to my value, the current content, the left child, and the right child. Some nodes have no children. We'll use none in Python to represent that. So this 7 node would look like this, a 7 with no left child and no right child. And this complete tree will be a much bigger nested tuple. At the top level, it's 1 tuple with 3 parts, a big left child, 5, my current value, and a big right child. And the left child and the right child also follow exactly the same layout. And we had suggested earlier that in computer science this is often called a recursive data structure. My tree, this 5, is made up of or contains smaller instances of itself, smaller instances that follow the same sort of pattern. So now let's get some concrete practice coding this up in Python. Let's try to write a procedure insert that takes one of these trees and a new element and returns a new tree including that element, just like you did in the quiz. So I'll just set things up. Insert takes a tree and an element. And this is going to be a recursive procedure. All the cool procedures are recursive. And the base case is actually inserting into the empty tree. If you don't give me anything to work with, I'll just make a new singleton tree containing only this element. And that looks like this. A singleton tree, just a single branch, has no left child, no right child, and the element right in the center. If the tree is not none, then it has a left child, a current element, and a right child. And what we want to do is compare the element to be inserted against the element we found here, and that will tell us whether we should insert into the left or insert into the right. I'm going to do this in 2 steps. If the element to be inserted is less than or equal to what we're currently looking at, then we're going to call ourselves recursively going down and to the left. So I'm going to call insert on the left child and try to insert the same element into it. And that's going to return a new tree, a new, minor typo, left child. I'll just build up a new tree that has the new left child, the same element that was here already, and the old right child unchanged. We never even have to look in the right child. We can ignore that half of the tree. That's a phenomenal cosmic boost to speed. This is an efficient data structure when done well. Otherwise, we're going to do mostly the same thing on the right. So here's a quiz for you. What should go in this blank?